Okay, so welcome to this afternoon's three talks. The first this afternoon, we're very pleased to welcome Akira Shudo from Department of Physics at Tokyo Metropolitan University. We're very grateful for taking the time for you to come to speak to us today. And the title of his talk is Time Domain Semiclassical Approach to Quantum Tunneling in Nearly Integrable Systems.
So thank you very much. And so first of all, I'd like to thank the organizer of the film and Chris for inviting me here. And it's a very great pleasure for me to hear. And so my talk is, my background is not a symptotic analysis, but my background is a dynamical system. So my talk is about the semiclassical approach to the quantum mechanical tunneling, because as you know, that quantum mechanical tunneling is an exponential small effect, so that exponential asymptotics appears in the evaluation of the quantum mechanical propagator, as I explained. So I first explain some background of my field and the problem I would like to discuss. As you know, that completely if the Hamiltonian has, in case where the 2 degrees of freedom, if the Hamiltonian has a 2 conserved quantity, then the Hamiltonian can be completely integrable. But if we perturb slightly to the completely integrable situation, then in general, the system becomes non-integrable. And here, so this is the typical form of a nearly integrable situation. And the tau is a kicking strength or a perturbation strength of in this situation. And if the perturbation increases, so here this is a completely integral the phase space. The phase space is filled by the invariant torus, and the torus, the motion of the torus is given by the quasi-periodic motion, which has 2 angular frequencies, omega 1 and omega 2. So that if the kicking perturbation strength increases, the phase space becomes much more complicated. And if further increase perturbation strength, phase space is filled by the chaotic trajectories. So we can capture that kind of aspect by taking so-called periodic kicked rotor, which is given by this. So this is a one-dimensional rotor perturbed periodically perturbed by a delta function. So this Hamiltonian, or the solution of this Hamiltonian, can be reduced to this type of the symplectic map, 2-dimensional area preserving map. We call the symplectic map here. So this captures the phase space aspect of the non-integrable situation. So this T is in a kinetic term, and the V is a potential term. So we can choose some. So typical choice of the T is P square, and the typical choice of V is, for example, in the sine or cosine. And if we increase tau from 0 to very small tau and tau equal 1, then we can realize the similar kind of phase space as in a continuous Hamiltonian system. So we investigate this type of simple map. So we call this is a classical dynamics. So this 2-dimensional map is written here is we call the classical dynamics. So there is some theorem by the Kolmogorov-Arnold model, which says that the invariant circle, which is given by the closed circle in the phase space, survive even if the perturbation tau is added, the perturbation term is added. So in case for the sufficiently small kicking perturbation strength, and also the irrational ratio of the rotation number of the angular frequency, so we can show that the invariant circle survives even after the perturbation is added. So this set of the curves is the remnants of the invariant curves in the completely integral situation. And And also, there is some theorem which is called the Poincare-Markov fixed point theorem, so which states that for irrational, not rational rotation number, so for example, in alpha is a ratio of the angular frequency, is given by some rational value. And this situation, so we have a kind of periodic orbit, a sequence of periodic orbit appears in the phase space. So here, this is a elliptic time periodic orbit, and this is a saddle time periodic orbit. That pair of the periodic orbit appears alternatively in the phase space. So this can be shown by the Poincare-Markov. So we call this kind of a chain structure in the island structure is a Poincare-Markov chain. So this structure appears in the previous slide. So here we notice that the Poincare-Markov chain appears somewhere in between the KM torus. So we can formulate the corresponding quantum mechanics by introducing a unitary operator, one-step unitary operator. And so eigenvalue problem for this unitary operator. So this gives rise to the eigenvalue equation given here. So the un is an eigenvalue, and phi n is eigenfunction. So these are typical examples of the eigenfunction in the phase space given here. And this is a phase space representation of the eigenfunction in a mixed phase space. Mixed phase space, I mean some mixture of the regular and the irregular motion exists in the phase space. So some eigenfunction is localized on the KM torus, and other eigenfunction, for example, localized in a nonlinear resonances, Poincare-Markov chains, and other eigenfunction is localized in the chaotic region. So this is a typical situation in eigenfunction, nature of the eigenfunction in the near integral situation. And when we see the same kind of eigenfunction in the Q representation, we project onto the Q plane, then we can see in case for the completely integral situation, so we can see that monotonically decaying behavior in the tunneling tail appears. So this sharp drop is a numerical artifact because of the discretization of the Q coordinates. So this is not important. So the important thing is that the tunneling tail can be written, it can be given by the monotonically decreasing tail. But in case of the nearly integral situation, so Poincare-Markov chain appears and the KM torus is deformed by the addition of the part-dimensional term. So the tunneling tail has some effect by the presence of the nonlinear resonances. So the decay normal monotonically, and so decay with humps, which is associated with a nonlinear resonance appears. So this is a typical situation of tunneling tail in the nearly integral situation. But still, the nature of the phase space of nearly integral system is very, very complicated. It's too complicated. So many structures appear in the phase space. KM torus survive, and the Poincare-Markov chain appears, and the other structures appears in the phase space. So therefore, our goal is understand the quantum mechanical tunneling in nearly integral system, but instead of considering the nearly integral system in general, but we concentrate on the ultra near integrable system I will show you later, instead of generic nearly integrable situation. And so I will show you that from quite naive quantum mechanical classical correspondence, one might expect that nothing happened if we see the ultra near integral situation, because if we remove any complicated structure from the phase space, then we can naively expect just a monotonical decay in the tunneling tail. But as we show that this is not the case, so this is an example of the ultra near integrable situation. So here we take TP is a kinetic term is taken by the P square, and the potential is given by the Q square minus cosine Q. This is in a typical on a near ultra near integrable situation. And we take the kicking perturbation strength tau is quite small. So therefore, we realize the phase space very close to the completely integrable situation. Here you can see nothing happened in the phase space. So phase space is covered, almost covered in a KM torus. So the Planck-Barkov chain doesn't appear, and the chaotic region doesn't appear in the phase space. So this is so we are now plotting the two types of plots. So one is the point generated by symplectic map. And another one is so 3BCH, I will explain here, is integral approximation for the map. So integral approximation is given by using the so-called Baker-Campbell-Hausdorff formula. So we can rewrite the symplectic map in this form into the sum operational operated expression given here. And we can apply the Baker-Campbell-Hausdorff formula to give some integral Hamiltonian. This is a integral approximation using the Baker-Campbell-Hausdorff formula. Then we compare the completely integral approximation with the classical mechanical time evolution. So here we superpose classical dynamics and the completely integral approximation. We cannot distinguish between two. So that means that the integral approximation is perfectly well. So that means that we cannot distinguish the completely integral phase space and a phase space generated by the symplectic map with small but a finite tau region. So then, we numerically calculate the corresponding eigenfunction. So this is the phase space of the ultra integrable situation. And so we can see that we also superpose the eigenfunction for the map and the integral approximation. So we cannot distinguish between the map and the completely integral approximation. Up to the, well, precision is the quadrupole precision. But if you increase the precision up to the 10 to the minus 100, 10 to the minus 200, then we can see some big difference appears in the completely integral situation and the non-integral situation. So this black curve is the eigenfunction for the map, a symplectic map, and the red curve is a completely integral eigenfunction. So here we can see that monotonically decreasing behavior is observed in a completely integral situation, but on the other hand, the map creates some very staircase step structures. So this is as I explained, that typically the conventional understanding of the tunneling is, as I explained, that the tunneling phase is modified or deformed by the presence of the nonlinear resonances. But in case there is no structure in the phase space, there is no nonlinear resonances, Planck-Barkov chain doesn't appear in the phase space. So nevertheless, the staircase structure appears in corresponding eigenfunction. And furthermore, there is a big difference between this type of the structure and this type of staircase structure, because in this structure, so there is, because this structure is associated with the presence of nonlinear resonances. So therefore, if we change the H bar, this structure doesn't move, even if we change the H bar. So because this structure is the position of this structure is determined by the position of the nonlinear resonance here. But on the other hand, so this case, so this staircase structure moves as a function of the h bar. So there's a big difference between the structure appears in a near integral situation and the ultra near integral situation. So there is an argument which is called the resonance assist tunneling, so which states that structures appears in the tunneling tail which originate from the classical structure. Classical structure means nonlinear resonances or other structure affect the tails of the eigenfunction. But this was discussed by these people. But in our ultra-near integral system, so the step structure appears in the tunneling tail, although the classical structure is invisible in the scale of the Planck constant cell. So usually a quite naive expectation is that if we take a quite large H-bar cell, then the large H-bar cell, so the structure is smeared out because of the uncertainty principle of quantum mechanics. So that we cannot expect any structure in a tunneling tail. But here, as we show, that the structure appears even though the size of the face in a Planck cell is much larger than any structure in the phase space. So this is one question. And another question is, as I mentioned, that that structure moves as a function of h bar. So this is an unexpected behavior which has not been shown in the resonance assist type argument. So we want to understand why such a structure appears in a tunneling tail in an ultra near integral situation. But the one big obstacle is that we don't have any semiclassical formula giving rise to an eigenfunction. So therefore, we switch from the eigenfunction problem to the time domain approach. So that's because we have the propagator. So propagator describes the time evolution of the time evolution of the wave function. And this is one option of the propagator, so which starts from some initial state, and we wait for some Q state. So well, representation does not so important, but so for example, we take some I state and we wait for the Q state. But in any case, the propagator is given by the multiple integral because we are considering the discrete time evolution. So therefore, this is a discrete analog of the Feynman path integral. So what we have to do is to evaluate this multiple integral. Then the tools we use is to apply the saddle point approximation to the given multiple integral. So this gives rise to the semiclassical approximation. So semiclassical approximation is achieved by applying the saddle point approximation for the multiple integral. So this is a typical behavior of the time evolution of the wave function. This is a numerical calculation for the time evolution, which starts from some minimal wave packet. And so this is a time step 63 and 94. So we have some periodic oscillation, which reflects the step structure appear in eigenfunction. So therefore, our goal is understand or interpret why that step structure appears out of the propagator, time evolution operator. And what is the classical or complex classical interpretation, why the step structure appears in a tunneling tail? This is the question I have. And so there are two aspects, quite important aspects. One is how classical disconnected regions are connected, because as I said, that there are a bunch of KM torus is covering in the phase space. So the region which is enclosed by the KM tori cannot go out or cannot get in. So therefore, the KM tori plays a role of the dynamic barrier it's like a barrier formed by the energy. So it's KM tori plays a role of a dynamic barrier. So how we can get into or get out from here to there, so it is only possible by using the complex dynamics. So we cannot get into by using the real classical dynamics. So I want to clarify the mechanism why such a transition occurs in a complex plane. This is one problem. And another problem is that we have to evaluate the quantum mechanical propagator by performing the saddle point approximation. So therefore, of course, the Stokes phenomenon appears because not all of the saddle point solution doesn't contribute. So therefore, we have to select which contribution survive and which contribution should be thrown out. So this is the second problem. So first I want to discuss something about some background of this complex classical dynamics. So there is many discussion about the study about the behavior of the dynamics in a complex plane, which is studied by the Bedford-Smiley from the 1990s. So they have published a series of papers about the behavior, the study of the complex dynamics in the two dimension. Two dimension is one example, is a simple map we are now considering. So there is a classification of the type of the orbit. The first type of the orbit is the orbit which goes to infinity. And this is denoted by I plus and I minus. And the second one is the orbit which stayed in the finite region. And the boundary of this, the set of the orbit which stayed in a finite region is called field in Julia set, And the boundary of the bounded orbit is called the Julia set. If we confine ourselves in a forward direction, then the Julia set should be called forward Julia set. If we take the backward, then we have to say that is the backward Julia set. And the intersection of the forward and the backward Julia set is called the Julia set. And so they show so many theorems about the behavior of the complex dynamics in two dimensions. And one important result, which is quite strongly related to our purpose, is the following. So take any periodic orbit in the phase space, either real or complex plane. Then closure, if we take the closure of the periodic orbit denoted by P, then this WSP is a stable manifold of the P. Stable manifold is, as is shown here, stable manifold is a set of the point which goes to some periodic orbit in the backward direction. And in the same way, the unstable manifold is a set of the point which goes away from the periodic orbit here. So these are the quite important invariant objects. And if we take the closure of the unstable manifold, then it gives the forward Julia set. And also, if you take the closure of the unstable manifold, then we get some J minuses and a forward and a backward Julia set. This is a statement given by the Bedford-Smiley. So I will explain what does it mean, what this theorem does it mean. So here, this is a schematic picture of the Planck-Barkov chain as I showed. And this is a typical phase space in a near integral situation. Here we take P is a periodic orbit, and we have another periodic orbit which is densely located on the real phase space. Typical one, here this is red one is another periodic orbit. Since this holds because of the Bedford-Smiley theorem, so therefore, if we take a stable manifold of periodic orbit P and take a closure, is equal to the closure of the stable manifold of P prime. So this share the same set J plus. So that means that if we start from somewhere in the vicinity of the periodic orbit P, this can come close to the periodic orbit P prime. So this theorem tells us that P and P prime is not connected in the real plane, but it always connected if we use a complex plane. So this is a statement by Beto and Smiley. So this is a numerical example showing that it indeed the case. So here we are plotting a stable manifold from the periodic orbit located here. So this is a projection onto the real plane. So we cannot get into the inside region because there are so many KM tori. So KM tori prevents its played role of the dynamic barrier. But if we go through the complex plane, here we show that. So this is a trajectories coming from the periodic orbit. Then this orbit, this is a trajectories which goes in a complex plane. This goes around and wrapping around at a fixed point in the center, and it goes to approach the real plane. And there is a periodic orbit in the real plane. So therefore, that orbit can reach from here to somewhere inside in the region. So that theorem by the Bedford-Smiley predicts that this kind of trajectory which connects any places, so the theorem guarantees the existence of such orbit which connects any periodic orbit in an unstable periodic orbit. So it means that in the case, if we confine ourselves in the real plane, we cannot get into and we cannot get out because of the dynamic barrier appears. But if we use the complex plane, we always get in any place, any place you want. So this is a kind of ergodicity in dynamics. So that means that in a real phase space, no ergodicity appears because many dynamic barriers exist. But if we go to the complex plane, even if the real plane is covered by many invariant objects, but always ergodicity is achieved. So there's a very big difference between dynamics in the real plane and the complex plane. So this is what the Bedford-Smiley theorem implies. So this is the summary so far. The one thing I would like to emphasize is that some very specific structure appears in ultra-integrable situation, although any structure cannot appear in the scale of the Planck constant. Planck constant is large enough to smear out any structure in a phase space, but nevertheless the structure appears in a tunneling tail. And in order to describe such a transition in a ultra-nearly integral situation, we have to have some ergodicity in the phase space. That ergodicity is guaranteed by the theorem by the Bedford-Smiley. So in case in a completely integral situation, so we have so this is the picture of the complexification of the KM torus. So in a completely integral situation, we can analytically continue to the complex KM torus anywhere we want. So therefore, we can bridge from this torus to this torus by taking a so-called instanton. Instanton is in a typical tunneling trajectories in an integral situation or 1D situation. But in case of the non-integral situation, no matter how small the perturbation strength, that analytical object is broken because of the presence of the natural boundary of the KM torus. So therefore, the KM torus is broken in phase space, and the natural boundary appears in the phase space. So therefore, there is no bridge like a completely integral situation. Then we have to use the ergodicity in a complex plane, as we showed. This is the one aspect of the complex trajectories. And So next subjects I'd like to discuss is how to evaluate, because we have to evaluate quantum mechanical propagator by using a saddle point approximation. The complex trajectory appears as a result or as a solution of the saddle point condition. So I'd like to discuss about how to deal with the Stokes phenomena by in evaluating the propagator given by the multiple integral. So our strategy is the following. So again, our goal would be develop a systematic recipe to finding a saddle point approximate saddle point solution that contributes to semiclassical propagator in a near integral situation. But as I emphasized, the generic nearly integrable situation is too complicated, it's too messy. So therefore, in this situation, not taking a not ultra integral situation, but we take anti-integral limit. Anti-integral limit is the opposite limit of the integral limit. That is, fully chaotic behavior is realized. That situation is called the anti-integral limit. So, of course, a completely integral system is a one ideal situation. But on the other hand, the anti-integral limit is the other ideal situation. So we start from the anti-integral limit and to see the behavior of the Stokes geometry, and then change the parameter gradually from the anti-integral limit to the near integral region. This is our strategy. I will show you. So the model, we want to discuss is about, this is a quantum mechanical propagator, and the saddle point condition gives rise to the in a classical map, which is given by in the Lagrangian form. So it is easy to show that this saddle point condition can be mapped to the simplex map by introducing some appropriate variable. And as a model system, then we take V of Q is given by the cubic potential. So if we take a cubic potential, this map is called the Henon map. So the map has the name of the Henon map. And the reason why we take this cubic map is because there is some classification by due to the Friedman Milner. So they show that there is a classification for the polynomial diffeomorphism. So they show that there is three kinds of polynomial diffeomorphism. And the first one is called the elementary map, and the second one is an affine map, and the third one is a Henon map. So the first two maps is very elementary or quite easy to understand, but the non-trivial map is given only by the Henon map. So therefore, so what we have to do is to analyze Henon map first. The non-trivial map is reduced. Every polynomial diffeomorphism can be reduced to the Henon map. So therefore, there's good reason to taking the Henon map. And another reason is, as we explained, that there is an anti-integral limit. It's quite good limit, which is realized by the so-called horseshoe dynamics. The horseshoe dynamics is the source of the chaos. So chaos appears as a result of the horseshoe dynamics is realized in the phase space. So in case, Henon map has one parameter, C, denoted by C. If we take C is large enough, then this type of the deformation or stretching and folding appears as a result of the one-step dynamics. So the shape is very similar to the horseshoe shapes. Therefore, so we call the horseshoe dynamics appears in this situation. So this is an ideal situation where the chaos appears. So if we take C is large enough, then the ideal chaos is realized in a phase space. So the reason why we take such an ideal limit is because if we draw the Stokes line this is Stokes line for the case in a C is not large enough. C is taken, for example, in the 1. So the phase space is covered by the chaotic region and the nonlinear resonance, and everything appears in the phase space. So in that case, this is a Stokes geometry. I skipped the detail of how we draw the Stokes geometry, but here we are plotting the ordinary tiny Stokes curves, and the ordinary Stokes curve is not active in ordinary Stokes curve, and new Stokes curve and the new Stokes curve not active. And also the ordinary turning point and the virtual turning point, which is introduced by the Okikawa Takei many years ago. And I follow the definition of these turning points and the Stokes curves and apply the definition to the multiple integral. Then we get this kind of quite messy Stokes geometry appears in general. So therefore, instead of taking the generic situation first, but we first study the anti-integral limit. So our strategy is, as mentioned, that we first see the completely horseshoe is realized in the phase space, and then change from C in the region where the C is large enough, and change gradually to the C equal in intermediate values. So this is the idea which is proposed by Civitanovich. His idea is applied for the analysis for the classical dynamics, and we borrowed his idea to analyze the Stokes geometry. So this is a time evolution of the Stokes line for the propagator. Since the map is given by the quadratic form, so therefore one-step iteration gives rise to the folding, once folding. And the propagator is given by the just single integral. So therefore the Stokes geometry or the propagator is essentially the same as the area function. So therefore the Stokes geometry appears in just the same as the area function. But if we iterate once more the two-step propagation, then so we have to do some stretching and folding twice. So therefore, doubly folded shape appears in a corresponding classical manifold. So correspondingly, this is a Stokes line, Stokes geometry for the doubly folded the horseshoe situation. So here we can see that the Stokes line, this is a Stokes line for the ordinary sense, and this intersect with each other in the real line. And we further step, this is this third step manifold, and corresponding ordinary Stokes line is given this. So we can see that the Stokes line is wrapping around around the origin. So if we increase the time step, the behavior is also much more complicated. This is the fourth step. In the case of still it's in a horseshoe region. It's the simplest possible situation, but nevertheless, the real ordinary Stokes curve is rotating around many times, and so it's quite messy. But fortunately, I cannot explain detail, but this horseshoe Stokes geometry for the horseshoe can be reduced to a kind of diagram. So this Stokes geometry is equivalent to this type of diagram. So making use of this diagram, so we can analyze any step, the structure of the Stokes geometry in any time steps. So we can manipulate the behavior of the Stokes geometry in the ordinary sense in any step. So then, so I skipped all the detail, but we can find that the number of the saddle point solution in the asymptotic region can be obtained by this formula. So this formula provides the number of the solid point solutions which survive in a asymptotic region. Asymptotic region means that Q is a variable of the final state, and if the Q is large enough, then so we want to know how many solutions appears and survive as a result of the Stokes phenomena. Then we can derive some explicit representation of the number of the solution which appears in any step. This is n is in a step of the function of the time evolution. Then so we get some the ratio. It's kind of entropy. Entropy is the growth rate of the number of the solution. One interesting thing is that this growth rate is represented by log alpha, and alpha is 1.46557. So this is less than 2. So this means that because the number of solutions increase exponentially 2 to the n. So therefore, if all the solutions survive as a result of the Stokes phenomena, so this should be log 2. But as you see, that alpha is less than 2. So that means that some cancellation, some systematic cancellation occurs. I will skip some detail, but we can have some recursion relation which gives rise to this type of number of the surviving solution. And as a result of the cancellation between the contributing saddle, then we get entropy which is less than log 2. So the systematic cancellation occurs as a result of some non-trivial geometrical relation. So then we get some growth rate in a completely integral situation. So then the next task is to change the parameters gradually. Since we established the Stokes geometry in any step in a horseshoe limit, so therefore next step is to analyze the Stokes geometry in any parameters. The C is not large enough, not necessarily large enough. Then the point is the following. So since we established the Stokes geometry, the nature of the Stokes geometry in a horseshoe limit, so therefore, so if we gradually change the parameter C, then the Stokes geometry graph, the pattern of the Stokes geometry changes gradually, of course, and at some point, some bifurcation occurs. So bifurcation means that in this case, this example is, so here this is two ordinary turning points is located in the real axis, and if you change the parameter gradually, so these two turning points collide with each other. And then after that, the two ordinary turning points fall to form some complex conjugate pair. Then this is what I call the bifurcation is a reorganization of the Stokes geometry. So this is an example for the time step 2. So this type of the bifurcation actually occurs, as you see that here we focus on this region. If we change the parameter C, then these two ordinary turning points collide with each other, and then it fall into the complex conjugate pair. So this type of bifurcation actually occurs in a Stokes geometry in a Helena. And another type of bifurcation is a bit complicated. So here we can see that the ordinary turning point is located again in a real axis, and we also find some bit degenerate crossing point. So 6 Stokes curves are intersect at one point, in the single point. And if we change the parameter C gradually, then this turning point moves to the left, and it goes through the degenerate crossing point. And then after that, so this degenerated crossing point dissolve. So this type of the bifurcation also found in the actual change of the reorganization of the Stokes phenomena, Stokes geometry in NL mapping. So, and it is not difficult to show that the type of the bifurcation which occurs in this situation is limited to these two types. The first one is a collision of the ordinary turning point, and the second type is the single turning point passing through the crossing point. There is only possibility. It's not difficult to show. That's because of there is some symmetry with respect to the real axis. That simplifies the problem, and we can show that the only possibility of the bifurcation is given by these two types. So, so based on this, so only these types of bifurcation, so we can generically show that. But if it is rigorously true, then with the change of the parameters, so the number of the contributing saddle keeps constant, because if we focus on the behavior in the asymptotic region, even if we have the bifurcation, so the number of the Stokes line in the asymptotic region doesn't change before and after the bifurcation. So therefore, of course, if we focus on the finite region, we have to take into account closely the bifurcation. But if we take into account only the infinite asymptotic region, the behavior doesn't change. Number of contributing saddle doesn't change because even bifurcation occurs and the Stokes geometry is reorganized, but the number of the solution in the infinite region doesn't change. So this greatly simplifies the problem, because since we know the behavior of the anti-integral limits, we can control the behavior of the Stokes line in anti-integral limit, and we gradually decrease the parameter from C equal to quite large enough to the small enough in an intermediate region. But the number of solution doesn't change, even if C changes. So my argument is a bit hand-waving, but so this is what we did so far. So now I summarize. So we studied the ultra near integral system because we cannot control what happened in a generic near integral situation, because many structures appear in the phase space is too complicated. So therefore, we limit ourselves to the very closely near linear system. So everything disappears in the scale of the Planck cell. But nevertheless, the structure appears. Structure appears because of the fact that the complex nature of the complex geometry drastically changes from the integral situation and non-integral situation, as I show you. The natural boundary appears, and this drastically changes the structure of the complex dynamics. And so the analysis of the Stokes geometry, so we take the anti-integral limit first, and then gradually changing the parameter, and then we get some region which is given by the near integral situation. So that is our strategy. That was our strategy. Okay, so that's what I want to say. Thank you very much.
Okay, anybody have any questions? I've got one. So on the type 2 bifurcation, as the turning point goes through the crossing point,
yeah.
Does anything special happen at that coalescence? I mean, you said that the number of Stokes lines don't change on either side, but does anything...
Coalescence of the turning point?
Yeah, and the Stokes crossing, and the crossing point.
Yeah, turning point just cross through the crossing point.
Yeah.
And no coalescence occurs in it.
But there's no change in the number of
No.
Stokes lines at that point. No?
Yeah,
No,
it doesn't change.
Okay.
That's why we can say that.
Okay. Yeah. Any other questions? The only other one I had was, how do you compute down to 10 to the minus 200? So, at the beginning. But
Okay.
Okay, all right, well, thank you very much, Akira. Thank you. And next up, we have Cecily Anderson from the University of Bath. So we'll just take a minute to change over. Yeah.
Did he answer?
I don't know.